Welcome to today's paper reading. Today's paper is titled, Transformers are SSMs, Generalized Models and Efficient Algorithms Through Structured State Space Duality. This paper was published on the AR14 preprint by Tri Dao and Albert Gu from Princeton University and Carnegie Mellon University. The abstract highlights the current landscape of deep learning models and language modeling. While transformers have been the dominant architecture, state space models, SSMs, such as Mamba have shown comparable or superior performance at smaller to medium scales. The authors establish a theoretical framework that reveals the close relationship between these model families, connecting them through decompositions of structured semiseparable matrices. This framework, termed state-space duality, SSD, enables the design of a new architecture called Mamba 2. This new model refines Mamba's selective SSM, achieving a significant speed improvement of 2 to 8 times, while maintaining competitive performance with transformers and language modeling tasks. The introduction of this paper highlights the significance of transformers, particularly decoder-only models like GPT and Llama, in modern deep learning. These models process input sequences causally and have driven significant advancements. However, the core attention layer in these models faces efficiency issues, such as quadratic scaling and sequence length during training. In contrast, structured state-space models, SSMs, offer linear scaling in sequence length and constant state size during generation, showing strong performance on long-range tasks. The paper aims to develop theoretical connections between SSMs and variants of attention, enabling the transfer of optimizations from transformers to SSMs. This includes the development of the linear attention framework and the introduction of the structured state space duality, SSD, algorithm, which leverages block decompositions of semiseparable matrices to achieve optimal efficiency trade-offs. Figure 1 illustrates the relationship between state space models, SSM, and attention through the lens of structured matrices. The structured state space duality, SSD, framework developed in this paper bridges these two models, enabling the transfer of optimizations from transformers to SSMs. This connection allows for the development of efficient algorithms for computing SSMs, such as the SSD algorithm, which is significantly faster than the selective scan implementation used in Mamba. The SSD algorithm leverages both linear SSM recurrence and quadratic dual forms, achieving optimal trade-offs and efficiency across various metrics. Structured state space models, SSMs, are a recent class of sequence models in deep learning, closely related to recurrent neural networks, RNNs, convolutional neural networks, CNNs, and classical state space models, SSMs. They are inspired by a continuous system that maps a one-dimensional sequence. The general discrete form of structured SSMs is represented by a set of equations. These models originated as continuous time maps on functions rather than operating directly on sequences. The matrices in these equations are not directly learned but generated from underlying parameters, with a parameterized step size. A discretization rule is then applied to convert these continuous parameters to discrete ones. State space models are used to represent dynamic systems with time-varying parameters through linear transformations. These models are often represented using structured matrices, which include sparse matrices, block diagonal forms, and Hankel matrices. The application of these models spans across various fields such as system identification, control theory, and signal processing. Understanding the structure of these matrices is crucial for efficient computation and accurate modeling of complex systems. State space models, SSMs, are shown to be equivalent to a family of structured matrices known as semiseparable matrices. This equivalence leads to new efficiency results, as highlighted in Theorems 3.5 and 3.7. The matrix transformation form of SSMs is derived, which simplifies the computation of these models. Semiseparable matrices, defined by rank conditions on their submatrices, have structured representations that enable fast algorithms for matrix multiplication. The computational efficiency of SSMs is achieved by reducing the problem to efficient algorithms for structured matrix multiplication. This includes both linear and quadratic modes of computation, with a focus on hardware-efficient implementations. Figure 2 illustrates how state space models can be viewed as a matrix transformation is an element of R, T, T, acting on the sequence dimension T. This transformation matrix is shared across each channel in a head, as shown on the left. On the right, it is depicted as a semiseparable matrix, a type of rank-structured matrix. This structure implies that every submatrix located on or below the diagonal, highlighted in blue, has a rank that does not exceed n, which is the state dimension of the SSM. This representation underscores the efficient computational properties of state space models due to their semiseparable matrix form. Figure 3 illustrates the concept of structured mass detention SMA. SMA constructs a mass detention matrix by combining the product of queries and keys with a structured matrix. This matrix defines a sequence transformation that maps values to outputs. The figure highlights that all instances of SMA have a dual form that allows for subquadratic computation, achieved by changing the order of tensor contractions and leveraging efficient matrix multiplication by. Examples of this approach include linear attention and RetNet. The figure also suggests that beyond the one semiseparable SMA, which is the focus of this paper, there are many other potential structured attention models that could be explored. In this section, we explore the duality between structured state space models and structured mass detention. Structured state space models, which are typically defined by linear time recurrences, can also be expressed in a quadratic form through matrix expansion. Similarly, attention models, which are defined by quadratic time interactions, can be reduced to a linear form through tensor contraction. A specific case of each model, where state space models have scalar identity structure and attention models have one semiseparable structure, demonstrates this duality with identical linear and quadratic forms. This duality is summarized in Figure 4 and further discussed in Section 10, which relates SSD to general SSMs and attention models. Additionally, Section 6 introduces a hardware-efficient algorithm for SSD models, enhancing their practical applicability. The algorithm presented in this section combines both the linear, recurrent, mode and the quadratic, attention, mode to compute SSD models efficiently. This approach ensures computation efficiency, scaling linearly with sequence length, and is hardware-friendly as it primarily uses matrix multiplications. According to Theorem 6.1, the algorithm requires O(Tn superscript 2) training flops, O(Tn) inference flops, and O(N superscript 2) inference memory, with the work dominated by matrix multiplications. The key idea is to decompose the matrix into diagonal and off-diagonal blocks. Diagonal blocks are computed using the dual attention mode, which is efficient with matrix multiplications, while off-diagonal blocks are factored by the rank structure of semi-separable matrices and reduced to a smaller recurrence. Figure 4 illustrates the duality between structured state space models, SSMs, and structured mass detention, SMA. On the left, it shows that both SSMs and SMA have both linear and quadratic forms, with direct analogs in notation. On the right, it highlights that SSMs and SMA intersect at a large class of state space dual models, SSD, which encompass many sequence models as special cases. This duality is crucial for understanding the computational efficiency and expressive power of these models. Figure 5 illustrates the SSD algorithm, which enhances the efficiency of state space model, SSM, computations by transforming them into semi-separable matrices. This approach involves a block decomposition matrix multiplication technique, where the matrix is divided into blocks representing chunks of the input and output sequences. The diagonal blocks handle computations within each chunk, while the off-diagonal blocks manage interactions between chunks, leveraging the SSM's hidden state. This method significantly improves hardware efficiency, making it a valuable tool for optimizing SSM computations. The Mamba 2 architecture introduces several key modifications. In block design, parallel parameter projections are adopted, which simplifies the generation of SSM parameters A, B, C, and X. An extra normalization layer is added to improve stability, similar to the normformer architecture. For multi-head patterns, the architecture includes multi-head SSM, MHS, multi-contract SSM, MCS, and multi-input SSM, MIS, which are analogous to multi-head attention patterns. Lastly, SSD extensions inspired by linear attention include kernel attention approximations, exponential kernel feature maps, and the incorporation of a normalization term to enhance performance. Figure 6 illustrates the Mamba 2 architecture, which simplifies the Mamba block by eliminating sequential linear projections. In Mamba 2, the SSM parameters are generated at the beginning of the block, rather than being a function of the SSM input. This change is accompanied by the addition of an extra normalization layer, similar to normformer, which enhances the stability of the model. Furthermore, then projections are streamlined to have a single head shared across the heads, a design choice analogous to multi-value attention, MVA. These modifications collectively aim to improve the efficiency and scalability of the Mamba 2 architecture. In this section, we discuss systems optimizations for SSMs, focusing on the Mamba 2 architecture. We start with tensor parallelism, TP, which involves splitting each layer across multiple GPUs. In the original Mamba architecture, this leads to two all-reduce operations, increasing communication time. The Mamba 2 architecture, however, is designed to require only one all-reduce per block, similar to transformer models. Next, we explore sequence parallelism, SP, which splits input and activations along the sequence length dimension. This technique includes reduced scatter and all-gather operations, and it is applied without modification to the Mamba 2 architecture. Finally, we address the challenge of variable length sequences. Instead of padding sequences to the same length, we treat the entire batch as one long sequence and set specific tokens to prevent information transfer between different sequences. These optimizations aim to enhance the efficiency of large-scale training and inference for SSMs. Figure 7 illustrates the parallelism strategies in the Mamba 2 block. On the left, tensor parallelism is shown where input and output projection matrices are split, and each SSM head operates on a single device. Group norm is chosen to minimize additional communication, requiring only one all-reduce per layer, similar to MLP or attention blocks in transformers. On the right, sequence/context parallelism is depicted, where the sequence dimension is split among multiple devices. Each device computes its sequence state and passes it to the next GPU, analogous to the SSD algorithm. Figure 8 illustrates the performance of Mamba 2 on multi-query associative recall, MQAR, tasks, which are particularly challenging for models like SSMs due to the requirement to memorize extensive information. The figure highlights that Mamba 2 significantly outperforms Mamba 1 across various settings, even when state sizes are controlled. This improvement is attributed to the larger state sizes enabled by the SSD layer in Mamba 2, which allows for better memorization of key-value pairs, thus enhancing performance on MQAR tasks. The empirical validation of Mamba 2 includes several key areas. Firstly, in synthetic tasks, Mamba 2 demonstrates significant improvement over Mamba 1, especially in the MQAR task. The increase in state size from n equals 16 to n equals 64 and n equals 256 consistently enhances performance, indicating the importance of state size for memorization. Secondly, in language modeling, Mamba 2 is evaluated on standard autoregressive tasks, showing competitive pre-training metrics and strong zero-shot evaluation results. The exploration of hybrid models combining SSD, MLP, and attention layers reveals that a balanced mix of these components yields the best performance. Lastly, in efficiency benchmarks, SSD is shown to be 2 to 8 times faster than Mamba's fused scan and faster than Flash Attention 2 starting at sequence length 2K, highlighting its computational efficiency. Table 1 presents the zero-shot evaluation results of Mamba 2 models across various sizes, comparing them against open-source language models with different tokenizers. The table highlights that Mamba 2 consistently outperforms Mamba, and it generally matches the performance of Pythia models that are twice its size. The evaluations are conducted on the pile validation split, focusing on models trained with the same dataset and tokenizer as GPT-NEO X20B. Detailed results are available in Table 10. Figure 9 illustrates the scaling laws for models ranging from approximately 125 million to 1.3 billion parameters, trained on the piled dataset. The figure demonstrates that Mamba 2 not only matches but also surpasses the performance of Mamba and a robust Transformer++ recipe. In comparison to the Transformer baseline, Mamba 2 exhibits Pareto dominance in terms of performance, measured by perplexity, theoretical flops, and actual wall clock time. Figure 10 presents efficiency benchmarks for the SSD algorithm. On the left, it demonstrates that SSD is 2 to 8 times faster than a Mamba fused scan for large state expansion, n equals 64, and outperforms flash attention 2 for sequence lengths of 2K and above. On the right, it shows that increasing state expansion linearly slows down the Mamba optimized scan implementation, while SSD can manage much larger state expansion factors without significant slowdown. Table 2 presents the perplexity results of a 350M model with 48 layers, varying the number of attention layers. The data indicates that a 10% ratio of attention layers yields the best performance in terms of perplexity. This suggests that a balanced combination of SSD and attention layers enhances model efficiency and quality. Table 3 presents the zero-shot evaluation results of various hybrid models combining SSD, MLP, and attention layers. The models are evaluated at a 2.7B scale, trained to 300B tokens on the piled dataset. The table highlights the best results for each size in bold, showcasing the performance metrics across different tasks such as piled perplexity, lambda perplexity and accuracy, Hellas-Wag accuracy, and others. This evaluation helps in understanding the effectiveness of different layer combinations in achieving superior model performance. Table 4 presents the ablation study of the Mamba 2 block, focusing on the major differences from the Mamba 1 block. The study examines the impact of parallel versus sequential projections and the addition of extra normalization parameters on model performance, as measured by perplexity. The results indicate that parallel projections save parameters and slightly enhance performance, while the extra normalization layer not only improves performance, but also aids in training stability. Table 5 presents the ablations of various multi-head structures for the Mamba 2 architecture. The table shows significant differences between multi-value and multi-query or multi-key head patterns, despite their apparent similarity. The models are characterized by a state expansion factor of equals 64 and a head size of equals 64, trained according to Chinchilla scaling law token counts. The number of heads is always equal to the total heads H, ensuring each head has a separate input-dependent decay factor. The results are presented for both 125M models trained on 2.5B tokens and 360M models trained on 7B tokens. Table 6 presents the results of ablating various proposals for the kernel activation function psi, focusing on linear attention variants designed to approximate the exponential kernel inherent in standard softmax attention. The table includes perplexity scores for different kernel activation functions, such as none, swish, exp, ReLU, and ReLU with normalization. Additionally, it covers specific implementations like cosformer, random feature attention, and positive random features, performer. These results provide insights into the performance of different kernel approximations in the context of linear attention mechanisms. Table 7 presents the results of ablations testing the RE-based methods for linear attention approximations. These methods involve expanding the feature dimension to improve linear attention. The table is divided into two sections, one for 130M models and another for 380M models with a state size of equals 256. The kernel activation functions tested include swish, swish plus Taylor, based, layer norm, and layer norm plus square, rebist. The table provides perplexity scores for each kernel activation function, indicating the performance of these methods in approximating linear attention. In this section, we delve into the related work and discussion surrounding the state-space duality framework. We first discuss state-space models, highlighting their characteristics such as time invariance versus time variance, dimensionality, and the structure of recurrent transitions. We then move on to structured matrices, where we explore matrix sequence transformations and the efficiency of subquadratic transformations, particularly through the lens of semiseparable matrices. Finally, we examine linear attention, noting its differences from standard attention, such as the absence of softmax activation and the use of an input-dependent one semiseparable mask, which provides positional information. These discussions pave the way for future extensions and improvements within the SSD framework. In this study, the authors proposed a theoretical framework based on structured matrices to bridge the gap between structured state space models, SSMs, and attention mechanisms. This framework provides insights into why recent SSMs like Mamba perform as well as transformers in language modeling tasks. Additionally, the theoretical tools developed offer new avenues for improving both SSMs and potentially transformers by integrating algorithmic and systems advancements from both domains. As a practical demonstration, the framework guided the design of a new architecture, Mamba 2, which is positioned at the intersection of SSMs and structured attention mechanisms. Thank you for watching.